Welcome to our relatively quick review of graphs, lines, and inequalities. We'll start by talking about the basics of some graphs. When the book refers to intercepts, remember that that's just their way of discussing solutions, right, for various functions. Something as simple as y equals 3x plus 2, a straight line. We know that if we graphed this, it would look something like that. Probably a little steeper, right? Slope of 3, and it crosses here at 2. The expression in x equal to 0 means looking for this point here. Where does it cross the x-axis? What value of x makes this thing equal to 0? And you could try and find it on the graph, but it's much easier to just solve for it algebraically, and you get negative 2/3. And they're just saying that, these solutions are the same thing as x-intercepts. It doesn't have to be a linear function. If you have a parabolic function and it crosses here at two places, those are still called the x-intercepts, and that is still those are both still going to be solutions for the function, right? Whenever you set the function equal to 0, that's basically saying when is the height equal to 0, and when you find those x points, those are x-intercepts. Okay, so x-intercepts are just solutions when you set something equal to 0, which is going to be very important because that's a lot of the stuff we're going to be doing in calculus. How about when we're dealing with lines, as we saw before with my first example? Well, we have to remind ourselves of some of the basics of lines. First thing is slope, how to compute it, and what does it mean, right? Your slope is just simply change in y over change in x, y2 minus y1, x2 minus x1. Sometimes they call it rise over run, right? It's got a bunch of different names, but it basically means the same thing. Delta y over delta x. That delta is the Greek symbol for change. If we have a slope of 0, that's a horizontal line, right? Vertical lines, the slope is undefined. Please do not say it has no slope. If you tried to ski down that, you would realize very quickly that it has a slope, right? We just cannot define it with numbers because it's vertical. Direction of the line, right? Horizontal is that 0. Upward gives us a positive slope, downward gives us a negative slope. So this is all should just be review of basic stuff. That's a positive slope, and that's a negative slope. And then of course this one's undefined. Two non-vertical lines are parallel whenever they have the same slope. Well, yes, but two vertical lines are also parallel. It's just the reason why we can't say when they have the same slope is because two vertical lines don't have any slope, right? The slope is undefined. So in essence, the slope is the same, right? They're both undefined. Basically, any two lines that have the same slope are parallel. Duh, you guys should know that. And then two non-vertical lines are perpendicular whenever the product of their slopes is -1. A little harder for me to draw because I'm not the world's greatest artist. But if you have the slope of this line and the slope of a perpendicular line to it, right? This is supposed to be a right angle. Then those two slopes are opposite reciprocals. If you remember, if the slope, let's say, of the first one is 3, then the slope of the perpendicular line is -1/3. And if you multiply those two numbers together, you get -1, right? If the slope of one line is 2/3, then the other one is -3/2. Again, you multiply them and you get -1. That's what this is telling us. And again, non-vertical lines, because a vertical line doesn't have an identified slope. But we obviously know that a vertical line and a horizontal line are perpendicular. Okay, the different ways of listing a line, just a lot of vocab. This one you're probably very familiar with, the slope-intercept form. Um, this one, maybe not so much. It's actually a very helpful way because if you're given a point, let's say 3, 2, and a slope, let's say -4, this formula is going to be the fastest way to get the equation of the line given a point and a slope, right? Point slope form. If you're given a point and a slope, then this is the fastest way to get the equation of the line. But guess what? You could still plug the point in here, right, into x and y, plug the slope into here, solve for b, and then rewrite the line again in just y equals -4x, and then whatever the number for b is, and you have it in slope-intercept form. So it only takes an extra step or two, and then you don't have to memorize a second formula, but you don't really have to memorize anyways, just put it in your notes. Same goes for all this stuff. Why waste brain space trying to memorize these things? Vertical lines, the only way to describe a vertical line is where it is located along the x-axis, right? Because they have undefined slope, so we can't define them by their slope. They don't cross the y-axis, so they don't have an intercept, so we can't describe them with their intercept. So the only way we can describe them is where they are left and right. So the only way to describe them is to tell us what x is, right? Where does it cross the x-axis? Same thing with horizontal lines. If we have horizontal lines, they don't have slope, so we can't describe them that way. They don't cross the x-axis, so we can't describe them with their intercepts, but they do cross the y-axis. They do have intercepts, so we can just list them as where is their intercept, or what value of y do they have. And then we've already talked about this one. We've already talked about this one. And then the general form of a line, not used a lot. You might come across it. It's really only used when you start doing linear programming and dealing with matrices. So, with that in mind, linear models, different from linear programming. We're still dealing with straight lines, only now we're dealing with the idea of regression, where we're taking a bunch of points. These are x, y coordinates. This is your input. This is your output. Input is always x, output is always y. It's not always that the top is x and the bottom is y. It really comes from the context of the question. In this particular question, you're trying to predict the credit amount. In this case, it's the amount of consumer credit outstanding. It's in trillions of dollars, so it's throughout the entire United States at one particular point in time in the year 1995, how much total consumer debt was there out there, excluding real estate debt, so they don't take mortgages into account. It's basically car loans, student loans, personal loans, credit cards, things like that. And there was a total of 1.1 trillion, this is in trillion dollars of debt in 1995, and you can see it's steadily going up. If we wanted to try and predict how much consumer debt there was in the year 2015, we could try to model this data. Now, in order to model it efficiently, instead of typing in x values of 1995, it's easier to just let the first one be our intercept. That's just going to be x equals 0. And then now this becomes 5, 7, 9, and 11, right? The number of years past 1995. Now, you wouldn't want to try and do this by hand, so it's much better to just bring in some technology. If you have a graphing calculator, great. If you don't, I would suggest either buying one or getting this free app. It's a thing you can get from the Texas Instruments website, and it allows you to use this kind of emulator is what it is. Okay, we turn it on. The first thing as it is, I put these numbers x and y in our two lists, and to do that you hit stat, edit brings you to lists, and then type them in your list. You have to keep them in order, right? 0 goes with 1.1, 5 goes with 1.7, so on and so on and so forth. Okay, once they're in the two lists, if we want to try and find the straight line that best models them, you go to stat, calculate, and then down here to linear regression, And you normally would need to tell it the two lists that you're going to use, but as long as your x's are in list 1 and your y's are in list 2, you can just hit enter and it defaults. This gives you the best line, right, that kind of fits our data. And you can see that according to them, A, right, is your slope, B is your intercept. So we got the line y equals 0.119 blah blah blah, or 0.12 if we rounded to 2 decimals, x plus 1.11. Well, that's exactly what they have here. And this is a slightly different version that they got with other computations. Now, if you had to figure out r and r squared, and this didn't give it to you, what you can do is go into your catalog, second 0, which brings up your catalog, and hit the X1 key for the D, and it brings you to the D part, because you can't really see, but there's a little tiny D right there. And what you're looking for is diagnostics. If you turn your diagnostics on and now rerun it, stat calculate linear regression, now it gives you everything, plus it gives you r squared and r. The other nice thing is you can graph all of this. If we go to y equals and go to vars for variables and go down to statistics, over to equation and reg equation, and hit enter, it's now put those numbers, those a's and b's, in here, and it's defined y by that. Now we can graph it. There's my line. You go, okay, well, that's great. What about my points? So how about turn our stat plots on, turn the first one on. We want to graph it as points. We're going to use list 1 and list 2, right? We're going to hit graph, and there's my line with my points. And in fact, I can even zoom into zoom stat, and now it zooms in on just the points in the line. You can see that line fits the points almost perfectly. So that's just a quick refresher on how to use your calculator to do all this stuff. There's plenty of YouTube videos out there that'll show you how to do this with more examples if I went too fast for you. Okay, on to linear inequalities. Again, to refresh our memory, the properties of an inequality is basically all the same as an equality except for one thing. So if we can add the same things and subtract the same thing to both sides of an equation, we can do that with an inequality. And that's what this first one is saying, right? That if you have A is less than B, then if you add the same amount to both sides, it's still the same. Also, A minus C is still less than B minus C. Now, here's the one slightly different thing. We know that if we have an equation, A equals B, then we know AC equals BC for all C's. But here we have a problem. If we have an inequality and we multiply both sides, the inequality is still the same as long as we multiply by a positive number. But when we multiply by a negative number, I'm sure you all remember we have to flip the direction of the sign. That being said, we also know that if we're dealing with an absolute value and an inequality, we're going to get two different situations. You don't need to memorize that. You can always just graph it, right? An absolute value function looks like that. So if you're looking for it being less than a certain amount, then you're looking for all of this, and that gives you something in between those 2 points. But if you have an absolute value function and you're trying to find out where it's greater than, right, taller than a certain point, then you can see that's going to be all that stuff in the two different directions. Polynomials and rational inequalities really are no different than any of the other inequalities. The best thing to always do with these is to graph them if you can, right? Graph your polynomial, and then if you're looking for it being greater than a certain amount, like greater than 0, you know it's all this stuff. Less than 0, you know it's the stuff down here. So in this case, you know it's the x's in between. If we're looking for greater, you know it's the x's on each side. If you're looking for less than, and so on and so on and so forth. So always graph if you can. That's the best way to do it. If not, you can use the calculator to help you graph it, right? And then above and beyond that, solving inequalities is really the same thing as just solving an equation. For instance, if you have something like 5 over x plus 4 is greater than or equal to 1, we'll just treat it as an equation, right? I mean, if you're trying to solve for these things, it's really no different than being an equation. The only problem is we know we can't multiply both sides by a negative, so we can't just multiply both sides by x plus 4 to get rid of this fraction, because we don't know if x plus 4 is always positive. So instead, the one major difference with rational inequalities is the only way to solve them is to set them greater than or equal to 0. So your first thing would be this: x plus 4 minus 1 is greater than or equal to 0. And now you have to make it one fraction. So you have to do a common denominator. 5 over x plus 4 minus x plus 4 over x plus 4. Right, we just turned 1 into this, greater than or equal to 0. Put all this together, you get 5 minus x minus 4, right? Don't forget that you're subtracting everything, so you're subtracting that 4 as well, all over x plus 4, greater than or equal to 0. So the top simplifies to negative x minus 1. Sorry, wrong. 5 minus 4 is positive 1. 1 minus x over x plus 4, greater than or equal to 0. Okay, now, in order for a fraction to be greater than or equal to 0, you figure out where it's equal to 0, top and bottom, and then you just check each interval. So on my number line, the top is equal to 0 at 1, the bottom is equal to 0 at negative 4. Okay? Now check each interval with a test point and see what happens. So here's my my fraction. Okay, pick a point in between these two numbers. Well, in between negative 4 and 1, the easiest point to choose is 0. If I plug 0 into this function, I get 1 over 4, right? Which is greater than 0. So it works here. Pick a number greater than 1, so just pick 2. If I put 2 into this thing, I get 1 minus 2, which is negative 1, over 2 plus 4, which is 6, and that doesn't work, right? That's negative, so no, fails here. Pick something in the third interval, something smaller than negative 4, so negative 5. You get 1 minus a minus 5, which is 1 plus 5, which is 6, and then negative 5 plus 4 is a negative 1. That's also less than 0, so it doesn't work there either. And then your solution is going to be all the numbers in between negative 4 and 1. Since this is a greater than or equal to, we can include 1, right? We'd put a square bracket here, because if it equals 1, we get a 0. But what about here? Is this going to be a square bracket? No, this is going to be a round bracket, because we can't let the bottom equal 0, because then it's undefined. So everything in between here, and you would write it negative 4 comma 1 with a square bracket, and that would be your solution to a rational inequality. Polynomial inequalities, they follow similar rules for regular linear inequalities. The only difference is now you have a polynomial. If you have something like x squared plus 3x plus 5 greater than or equal to 7, similar to these, the only way you can solve polynomial inequalities is to set them greater than or equal to 0, kind of like the picture. So you'd move the 7 over, and then solve. And the only way to solve for a polynomial being greater than or equal to 0 is to get it in the form of a times b, right, greater than or equal to 0, because now a product is equal to 0 when either of the numbers are 0, and we can know when it's positive, right, in this case positive, if they're both positive or both negative. So you would do the same thing. You would have to factor it. let's just say, I change these up. This is wrong, but just to make it easy so we can see what happens. Let's say this is, x minus 2x plus 1. Okay. Then on the number line, your zeros are at -1 and +2, right? Because this a 0 of 2 and a 0 of -1. And then you would test each of those things with test points, just like we did down here. Same technique. Okay, that's everything you need to know for this review session.